Okay, good morning, everybody. This is chapter 13, the properties of mixtures, which basically refers to solutions and colloids. We will not be discussing colloids here in this chapter, so we will be focusing primarily on the properties of mixtures as solutions. Now, I am going to basically start with section 13.5, which is the concentration terms, and I will basically talk about five main concentration terms, also known as concentration units. So if you come across anywhere that they discuss concentration units, they are the same thing: concentration terms and units. Okay, so these five concentration terms, they refer to basically quantitatively how much solute is dissolved in a given solution. Okay, we will come back to the definition of solution, solute, and solvent later. But right now, let's just start with the first concentration term, which is molarity. You've probably seen this in General Chemistry 1, that molarity is defined as the moles of solute divided by the liters of solution. So if you want to put it in the form of an equation, molarity is shown by the letter M, capital M, and then mole divided by L. So mole stands for moles of solute, liter of solution, and M is molarity. So basically I'm referring to this equation here. So this is an important equation that you need to memorize. So from now on, everything that I place in a box, those are important equations that need to be memorized. So you're going to refer to this as equation 1, the equation for molarity. Now, as an equation, we can basically play around with it. So moles can be obtained by cross-multiplying molarity by liter, or liter can be calculated if you divide the moles by molarity. The second concentration unit or concentration term is called molality. Molality is symbolized by the lowercase m, and it's defined as the moles of solute divided by the kilograms of solvent. So therefore, in the form of an equation, like previous case, we write it as moles divided by kilogram, where it's understood that the denominator now refers to the kilogram of the solvent, okay? And again, the moles can be calculated by multiplying molality and kilogram, and kilogram can be calculated by dividing moles by the molality of the solution. So again, this equation also needs to be memorized. So these are the two master equations: how to calculate molality and molality. Okay, please do not confuse the units and the symbols for each concentration term. So lowercase m refers to molality, and capital M, moles per liter, which is molarity. Okay, so it's important to distinguish the two. Okay, now let's go to the next slide. So, as I mentioned previously, solution is defined as a solute plus solvent. So solution is basically made of two components. The one component that is present in lesser quantity is called solute. And the other component that is present in the larger quantity is referred to as the solvent. So, for example, when you dissolve a certain amount of sodium chloride, in this example 20 grams of sodium chloride, in let's say 500 milliliters of water, we have an aqueous solution of sodium chloride. And I'll also define what aqueous is, because from now on we are going to refer to this term quite frequently. Aqueous solution, or AQ solution, is a solution where water is mainly the solvent. Now, the other concentration term that I've defined here is basically called mass percent, also known as percent by mass. Okay, so mass percent by mass, they are the same thing. So mass percent is defined as the grams of solute divided by the grams of solution times 100%. Remember, the gram of solution now refers to the total mass of the solution, which is the mass of solute plus the mass of solvent. And don't forget that this ratio must be multiplied by 100% to give us the mass percent. Okay, now in the next slide we take a look at some other information related to concentration terms. Another concentration term that we're going to define here is called volume percent, which is defined similarly to the mass percent. Now, instead of taking the ratio of masses, now we're taking the ratio of the volumes of solute and solution respectively. So basically, volume percent is the volume of solute divided by the volume of the solution times 100%. And I'm writing VOL for volume. Now, mole fraction is another concentration term that is important, and quite frequently we are going to refer to or calculate this quantity in various problems here in this chapter. Mole fraction, or X, that's the symbol that we use for mole fraction. Is the mole of solute divided by the mole of solution. Now, in all these quantities or equations, the term solution again refers to a total mass or mole of solute plus solvent. Okay, so when we have solute and solvent added together, the solution is obtained. That is the basic definition of the solution as mentioned previously. So when we say the mass of solution, the moles of solution, that basically means the moles of solute plus the moles of solvent. Okay, so always think of solution as a total quantity made of two components, solute and solvent. Okay, now, so basically right now we have defined 5 concentration terms: molarity, mass percent, volume percent, mole fraction. I want you to memorize the equation for each given concentration term. Okay, now also I wanted to mention that in many textbooks they talk about mole percent. Mole percent is really mole fraction, this quantity here, multiplied by 100%. So when you take this ratio and multiply by 100%, you get mole percent. Okay. Now, let's go to the next slide. Okay, so now that we have defined all these concentration terms, the question is, how do we use these terms in practical applications, in calculations, basically, in chemical calculations? How do we use them? Okay, so the first thing was to define them in the form of an equation. And then the second thing that we want to do right now is to go over these equations and see how we can apply them in calculating various properties of the solution. Okay, so the first problem is sample problem 13.4. And by the way, I'm using right now the 8th edition of the textbook, the chemistry by Silberberg and Amatis, the molecular nature of matter and change. That's the 8th edition. So all the problems, or the follow-up problems that I'm citing here in these lecture videos, they all refer to the 8th edition. Okay, so this is sample problem 13.4. The question is, what is the molality of a solution prepared by dissolving 32 grams of calcium chloride in 271 grams of water? Okay, so if you want to calculate the molality, the two things that we need, according to the defining equation of molality, is the moles of solute, meaning here the moles of calcium chloride, and the kilogram of solvent, basically being water here. So we need to convert the 32 grams of calcium chloride to the moles of calcium chloride and 271 grams of water to kilograms of water. Okay, now in order to convert the moles, in order to convert the grams to moles, we need the molar mass. because you remember that when you divide the grams by the molar mass, you get moles. That's basically from General Chemistry 1. So the molar mass of calcium chloride is 110.98. Now that is something that you obtain from the periodic table by adding the molar masses of calcium and 2 times the molar mass of Cl. That number is 110.98. So 32 divided by the molar mass gives you the number of moles of the solute, which in this case is calcium chloride. And also, since I need the kilograms of water, I divide this number by 1,000 to get 0.271 kilograms of water. Remember, grams divided by 1,000 gives you kilogram, and also the grams of solute divided by the molar mass gives you the moles. Okay, so I've put a little note here describing this process, that 100.98 is the molar mass of calcium chloride, which is obtained from the periodic table. So on the exam, these molar masses will be given to you. Okay, in the next slide, we are looking at some basic conversion that it's basically a refresher. You are supposed to know this from General Chemistry 1, but I've indicated here, just in case you've forgotten it, that when you divide the grams by the mm stands for molar mass. That is the number that you get from the periodic table by adding the molar masses of individual components. So if you divide the grams by the molar mass, you get moles. If you multiply the moles by the molar mass, you go back to grams. And also a similar conversion chart here for grams to kilograms, kilograms to grams. So if you divide the grams by 1,000, you get kilograms. If you multiply the kilograms by 1,000, you get grams. Okay. Now, I always like to include follow-up problems when we work on a sample problem, so that it reinforces the concept more effectively. Now, the follow-up problem is 13.4a, 13.4b, which is right after the sample problem we just discussed. Now, another problem, which in this case is a follow-up problem, and it's a follow-up problem 13.5a, that discusses the other concentration terms, mass percent and mole fraction, is outlined here at the bottom of this slide. We have an alcohol that contains 35 grams of 1-propanol and 150 grams of ethanol, 2 different alcohols. Okay, so they make up that solution. Now, I also need to emphasize the fact that not all solutions have water as the main solvent. Some solutions, they have organic solvent as the solvent for the solution. So it doesn't necessarily have to be water. So the question is, in this problem, what is the mass percent and mole fraction of each component? Okay, so we look at the equation for the mass percent. The mass percent for example, the 1-propanol is going to be the mass of 1-propanol, 35, divided by the total mass of the solution, okay, which is the propanol plus ethanol, times 100%. And the mass percent of the other component is going to be, which is ethanol, is going to be the mass of ethanol, 150 grams, divided by the total mass, times 100%. Okay, now, in your textbook, I have done this individually for each component, but in your textbook, the author calculates the mass percent first, 18.9% for 1-propanol, and then he does 100 minus 18.9 to get the mass percent of the other component, which is equivalent to this calculation. But that's a shortcut. Basically, this is a shortcut, so you can do the same thing, because the sum of the mass percents must be equal to 100. So if you calculate the mass percent of one component, the other component is going to be 100 minus that number, okay? So that's what you can do here, Okay. Now, in the next slide, we are going to take a look at the mole fraction. So basically, that's part B of the same problem. What is the mole fraction of 1-propanol? Okay. Now, in order to, or what is the mole fraction of ethanol? So the mole fraction, in order to calculate the mole fraction of any component, you need the molar masses of the solution, and you need the molar mass of that particular component. So I have provided the molar masses here for you, 60.09 for 1-propanol, 46.07 for ethanol. So these are the numbers that we get from the periodic table. So again, if you divide the mass by the molar mass, you get the mole. Okay, so that's what I've done here. Okay, so I have the moles of C3H7OH, the moles of C2H5OH. Okay, so the mole fraction of, so you can basically calculate these numbers and substitute them in this equation here to get 0.152. Okay, now, one important thing about the mole fraction calculation is that the sum of the mole fractions of all the components in a given solution must be equal to 1. So this is true for all mole fractions, because after all, they are fractions. Fractions, they add up to give you 1. So if you calculate the mole fraction of one component, again, we calculated that to be 0.152 by substituting these numbers in this equation, then the other component is going to be 1 minus the mole fraction of the component that you just calculated. Okay, so basically we calculated that to be 0.152. 1 minus 0.152 gives you the mole fraction of the other component. Okay, so it's pretty much like the mass percent calculation. Once you calculate one, you can calculate the other one easily. Okay, now the next section is called interconverting concentration terms, or ICT, interconverting concentration terms. Now, in this section, we are usually given one concentration term, only one. Maybe molarity, maybe molality, maybe mole percent, volume percent, or maybe mole fraction. Only one concentration unit is given. And then we are asked to calculate the other concentration terms. Now, I have included an example here, which is 13.6 on page 556. Again, I'm referring to 8th edition of the textbook. And that is basically an aqueous solution of hydrogen peroxide, which the formula for it is H2O2, not H2O, H2O2. And the solution has water as the solvent because it's an aqueous solution. So H2O2 is dissolved in water, and it's 30% by mass. In other words, the mass percent of that solution is 30%. And the density of the solution is 1.11 gram per milliliter. And the question is, what is molality, what is molarity, and what is the mole fraction of H2O2? So this is basically a typical interconverting concentration term problem. Okay, so now let me just make sure this is straight. Okay, now one thing about interconverting concentration term is that depending on what is given to us in the problem, we have to make some simplifying assumptions to be able to work the problem. So, for example, if the mass percent is given, like this problem, the mass percent is 30. If the mass percent is given to us, then the simplest assumption we can make is that the total mass of the solution is, or the total gram of the solution is 100 grams. Okay, because once we make that assumption, the grams of solute becomes automatically equal to the mass percent given to us in the problem. So if the mass percent is 30% and we assume we have 100 grams of solution, remember, gram of solution refers to the gram of both components, then we automatically know that the grams of the solute is 30 grams, and the grams of water is going to be 100 minus that. 100 is the total mass of the solution, right? I'm just basically using this equation. If this is 30, then the grams of water is going to be 100 minus 30, right? Which is 70 grams. So again, by assuming 100 grams, we're simplifying the problem by basically taking the mass percent to be the grams of the solute, okay? Here. Now, and once we have that, then we can calculate the mass of the other component using that, okay? Using the equation that 100 minus the mass of one will give you the mass of the other one. Okay, so now that we have the mass of all these components, we should be able to calculate the number of moles by dividing the grams by molar masses. So remember, we have 30 grams of hydrogen peroxide, 70 grams of water, and now we convert them to their respective mole numbers by dividing by the molar masses. 34.02 molar mass of hydrogen peroxide, 18.02 molar mass of water. Again, these numbers will be given to you, and we calculate the moles. So the molality of hydrogen peroxide is going to be moles divided by kilogram of water. So I have 0.882 moles of H2O2 divided by 0.07 kilograms of water. Remember, we have 70 grams of water, but we need to convert that to kilograms of water. So basically, we divide that 70 grams by 1,000 to get this number, okay? So we get 12.6 molality for the solution. So I've indicated that here, that the kilogram is 70 divided by 1,000. Okay, now, in the next slide, we calculate molarity. For molarity, we need what? We need moles, which we already have, moles of solute, and we need the liters of the solution. Now, in order to calculate the liters of the solution, okay, we must use this equation here that the volume of the solution is equal to so the density is mass over volume, but the volume of the solution is going to be mass over density. So the total mass is 100, the density of the solution is 1.11. Now 100 gram is what we assume, the density is given to us, so we get the volume of the solution to be 90.1 milliliters. But this is milliliters, this is not liters, so we have to convert this milliliters to liters, and we divide that by 1,000. So again, milliliters divided by 1,000 gives us liters, okay? So molarity would be the moles, which we already calculated, 0.882 divided by this number in liters, and that will give us the molarity, which is 9.79. Now, the last part of this problem is to calculate the mole fraction for hydrogen peroxide. Now, in order to calculate the mole fraction, all we need is the number of moles of various components, which is H2O2 and water. And we already have calculated those numbers in the previous parts for this problem. I think it was part A. So we just basically plug in the numbers. Moles of H2O2 divided by moles of H2O2 plus the moles of water, that will give us 0.185. And remember, all mole fractions must be less than 1 because these are, after all, fractions. So if you get a mole fraction that is greater than 1, then you know you have made a mistake. So all mole fractions must be less than 1. And I've explained that here, and I've wanted to underline some key words here. All less than 1, and they are fractions, so they cannot be greater than 1. And also don't forget that the sum of the mole fraction of the various components, solid plus solvent, gives you 1. And I want you to get more practice related to interconverting concentration terms. I want you to work on 13.6a, 13.6b, and we will discuss the next topic, which is colligative properties, in the next video.